We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
All right. My name is Kostis Maglaras. I'm the Dean of the Business School, and normally I get to pick who comes before me when I come to talk, and I don't quite know how I'm going to follow what we just experienced. But it's wonderful to have you all here, and it's wonderful to be capping a wonderful day with what we're going to be treated over the next 45 minutes or so. I want to make a few comments, and I'll punctuate it with a story that I was telling Scott when he and I met. But I want to sort of start by talking about Think Bigger and what all of you have been doing all day today, and sort of bringing together incredible individuals from academia, from industry. You cannot hear me. Is that what I just heard? Let me just bring myself closer to the mic. So it's incredible to be bringing here academics, practitioners, policymakers, to truly think about vexing problems that face our society, face businesses, and what you've been engaging in today is part of the activities that we're organizing through something that we call the Hub. When we moved here in the business school, in this beautiful campus that we opened up in about 15 months ago, we created a small think tank. We call it the Hub. We may change the name at some point in time in the future, but that's its current name. And the idea there is to bring people together to really think about areas of work that are fundamentally important to the future of business education and the practice of business. And the thing we've been grappling with are things that lie on the interface of business and society. And I think a lot of you today have been talking about concepts related to that and fundamentally about innovation and creativity and how, we can sort of come up with incredible new ways of thinking about problems and then scaling solutions and thinking about how not only how to do it in small organizations, but also how to do it in large organizations that have a lot of inertia, but they also have the ability to scale and have real impact. And I think it's wonderful. Our speaker today is going to sort of truly allow us to peek into the unknown and into the past in some sense, and truly allow us to experience something about the secrets of our universe. And before I introduce him and then get out of here to sort of let him give his exciting presentation, I want to ask, how many people here actually thought or dreamt of going to space or doing things like that when they were growing up? Okay, all right. I kind of knew that I wasn't going to be alone in that. So I told Scott that when I was growing up, I grew up in Athens, and I also wanted to go to space. And then, you know, my sister was a few years older than me, kept making fun of me. He's like, listen, you know, you're growing up in Greece. There's no way you're going to go to space. So just change your plans. So I remember I was, you know, 8 years old, 9 years old. I'm like, okay, maybe I'm going to try to become a scientist to send people to space, okay? So I almost succeeded with that, as I was telling Scott, because I actually worked in my PhD in electrical engineering, more or less started working in dynamical systems and guidance systems. And had I been a US citizen, it could have been that that would have been my path, because that was my research and that was what I did my dissertation. But, you know, I wasn't a US citizen when I came here, so I ended up working on different dynamical systems. And before you know it, you become the dean of a business school. But, so I didn't go to space. So Scott Willoughby is a true leader and a pioneer of the aerospace industry. He has worked there for more than 3 decades and building extraordinarily complex, I would say, feats of engineering, okay? These are incredible equipment, machines that solve incredible problems that are very difficult to even begin to think, complicated in their sort of design, their engineering, their manufacturing, and he's done that for 34 years. The latest and greatest is being the program manager and vice president for NASA's James Webb Telescope, which we just saw a few minutes ago. He oversaw development, testing, integration of the telescope on behalf of Northrop Grumman, this incredible company that was a primary contractor for the telescope. The telescope, of course, is our ability to have a time machine to look into the past and look at how worlds were looking billions of years ago and try to then sort of build our understanding of the universe and sort of build it to explore our future in the context. So I think this is just fascinating and incredible, and the level of ingenuity that happens to actually achieve such a thing is something that is daunting and humbling. My office back at Stanford was right next to an experiment that some of you may have heard. I know Scott had heard it. It's called Gravity Probe B. This was a 35-year experiment, something that has to do with dark matter, okay? And as a side product, they invented the GPS along the way, okay? But these are incredible feats of science and engineering, and that's exactly what Scott has done. So Scott, the floor is yours, and we're all eager to hear what you have to say. Thank you.
Well, this is humbling, to be able to connect with an audience. And in the concept of what you're talking about, thinking bigger, I'm going to show you something a lot in the scale. And when I had an opportunity to read Sheena's book before it was released, it was inspiring me all over that the journey never stops, right? Now I'm going to talk to you. I'm going to go back in time. I'm going to bring you to the present. I'm going to actually show you the future we're doing here. But thank you, Dean. It's wonderful. I appreciate the warm welcome here. There's others who I knew who had helped set this up, Ryan McNamis, and you would thought that was the easier name to pronounce, and Professor Roger Cabal, and I probably messed that one up too. But key in here, Doug Main is the contact that everything that you never know what happens in life when you say yes to something. So let me encourage you all when you get asked to do something, which was at a request through our comms folks to give a talk in upstate New York that has now built a connection that has brought me here to Columbia Universe. And when you leave here, you have information now that'll help you more readily connect to other folks, because I ask that you all share what you hear tonight, and then you just keep amplifying the story. So it's wonderful. And Professor Iyengar, and the joy that I had to be able to read the book before others did, I privilege, and to have a quote on the book cover gets me to lord that over my children for the rest of my life. I get to point to the back of that book on the bookshelf and say, come on, is Dad cool yet? I'm under Satya Nadella, the CEO of Microsoft. I'm just number 2 on the back cover here. This is pretty cool stuff. So this summit is so appropriate to what has impassioned me my entire career, and to a great degree is embodied in this telescope. And I really want to show you what it meant to get here, and this should really start firing synapses and connecting what you've been hearing in the last few days here. So let's go on to our New York City cosmic voyage here. And just to confess, if you haven't heard my accent, I'm on the other side of the river in New Jersey, but this is a bit of a coming home for me. So I really appreciate the audience here. So starting with a picture here that behind me is the iconic Webb mirror. It's a mirror that's going to answer the questions, where do we come from and are we alone? And in the nature of what we're going to see in that mirror is something that is going to inspire generations time and time again. The hopes and dreams of Webb, though, were built on something that has never been done before. A series of things that have never been done before. And it was also something that we did in the light of the public. So as many great articles as you read about Webb now, if you Google our name, you're going to find a handful of more interesting things out there as we were suffering. And I don't know that anybody, because it probably wasn't invented yet, was sitting in Edison over his shoulder criticizing every failure in the midst of all the amazing inventions that came. But we lived this in the public intentionally so, because every story is greater if you know the journey and if you know what it took. Otherwise, you could have just said, oh my God, Webb, NASA built this great giant telescope and it's doing something, and almost dismiss what it took to happen because you just expect those things. And we were talking before, your generation now, you expect rockets to launch every day, right? And watch SpaceX launch a rocket and just land it back on Earth. It's commonplace, where that was inspiration, right? Not decades earlier. What we're doing is going to be a consistent of what I'll say setting the bar for revolution, not evolution. And there was a team of people that had to build this. In the end, this was on the backs of folks, and I'm going to share a little bit about how broad that it was. And that's why in this picture, and in many of our pictures, not all of them, certainly not the ones that are in deep space 13 billion years old, but the ones I show you on ground, I always try and have people in front of it. So you get a sense that this was created by humankind. And there's a lucky person. I never got to do that in my job. They wouldn't put me in a basket and send me in the mirror. As a matter of fact, of my entire time of 12 years managing the program, I never touched the James Webb Space Telescope because I'm a manager and I should not be near hardware. It's really a big disappointment to me that I can't say I didn't touch the James Webb Space Telescope. So let's talk about the beginning. And to the degree that you hear the stories of inspiration, but realizing inspiration is important, but it isn't a spontaneous act where inspiration becomes product, right? It's built, and I'm going to share some stories of a convergence of things, call it in the whole cloth of engineering, but from outside of that, right, from other things. But, the apple falling on the head to Newton is drawing on a cocktail napkin in our day and age, right? Because we're drinking more when we're coming up with smart ideas. And Webb started on a cocktail napkin to a degree in 1986. So Garth Illingworth in particular, and Riccardo Giacconi, who was at the head of the Space Telescope Science Institute at that point in time, before Hubble launched, were already having a vision of what they wanted to do that was going to be greater of what they anticipated Hubble would. And Hubble is an iconic name as NASA is at this point in time. Everybody knows it. You see the imagery. You put it as you're on your screensaver until you put it over with the Webb imagery now, right? But you didn't have to be an astrophysicist or an astronomer to be in awe of the pillars of creation or the Horsehead Nebula or the things that, they were convincing that what was a dark piece of sky has 10,000 galaxies in it, right? Which is mind-numbing. And that journey went on. It went on eventually to Dr. John Mather, who's the Nobel Prize winner with George Smoot, on basically the age of the universe going back to the cosmic microwave background energy in there. And John furthered the idea and said, it's actually capable for us to answer the questions, where do we come from and are we alone? He said this with his bling of a Nobel laureate, that this can be done. And then the person who really took that mantle was the head of NASA at that point in time, Dan Goldin. And you would think NASA aspires and inspires, right, to do things never done before. But even then, the NASA engineers were a little bit worried about thinking too big. They thought of a bigger Hubble, basically. Hubble is a 2.4 meter optic in diameter. Let's make it 4 meters. Well, why bigger? That's better. Why did they stop at 4? Well, they stopped at 4 because the only thing you can get off of Earth has to fit in a 5-meter fairing, the thing that protects us from Earth's atmosphere as you launch. So you got to be smaller, right? There's things around the edge and all that stuff. So they stopped at the limitation that was handed to them by the top of a rocket. And Dan Goldin said, nope, I know a company who can do something that's bigger than the top of that rocket. We'll just build a mirror and we'll fold it up. And that company was TRW back in the days, who he happened to be a vice president of before, and then a company I hired in 1989 that won the prime contractor for Webb. But it showed where there was folks, even the most inspired of folks, stopped at what they thought was a threshold, and then somebody pushed them over. But it still had to be translated into reality. And what's it going to do? These are just 4 simple mission statements that really sum up into where do we come from, are we alone? But, how did the early universe form, right? Stars are the engine which everything else now is born of. And let me just tell you, for all the folks in here that maybe wanted to be engineers and didn't like chemistry in class, if you were only 13.5 billion years old, you'd all pass chemistry. Imagine that. You'd have less hair like me because you'd be really old, but 13.5 billion years ago, after the Big Bang, the periodic table had built itself to elements 1 and 2. Hydrogen and helium. Why do we have carbon and oxygen and iron? And why did we, eventually get heavy metals like gold and platinum? Well, because stars formed. And what's a star? It's a fusion reactor. It sums things up. It literally burns helium and hydrogen as a fuel. And the result of it is building a periodic table. So imagine, if you're a parent, having your child's life, from birth to, sometime in the crib, and then eventually the kid's already walking and going to school, and there's a chapter in there missing. How did that kid learn how to stand up and start spouting out some words in there? That chapter is missing because we didn't have an eyeball big enough and sensitive enough to see that, which is now the James Webb Space Telescope. So again, you only wish you were all be chemical engineers, right, if you were just 13.5 billion years old. Thank goodness for those stars, because things are a lot more complicated now. But the elements that form us and our planet all came from that beginning. As humans, we never are going to stop our curiosity. We want to know what happened. So in terms of invention, what made this such an audacious project are some of the things that we're talking about here. I hope the microphone's still projecting with this fun thing in my ear here. So we had to build something that has to now fold up. It has to go into the top of a rocket, which I mentioned is still limited by 5 meters, 16 feet across. The mirror itself is 22.5 feet across, 6.5 meters. Underneath that is a sun shield the size of a tennis court, enabling this optic to run at minus 400 degrees Fahrenheit. Why? Because we're using infrared to find this old light. I'll share that in a science story later. Infrared, though, is why night vision goggles work. Why, if all the lights were out, I'd find you in this room, because you emit infrared. Everything's emitted infrared. Well, that just blurs out the starlight from 13.5 billion years ago. If you're not colder than what you're looking for, you see yourself in terms of an instrument. So we had to make this thing huge. We had to make it cold. We had to make it very stable. I'm going to share a little bit of that in the science, how stable this is. And then we had to fly it 1 million miles away from Earth. 1 million miles away, 4 times further than the moon, 4 times further than humankind has ever been of our planet. Again, if you've just been around since 1990 and forward, you know Hubble was serviced by astronauts. They went up there, they grabbed it. First, they had to fix it. Then they improved it. 5 service missions. I've met several times. I've had dinner with the last human being to touch the Hubble Space Telescope, Dr. John Grunsfeld. If you watch the IMAX movie and he kind of salutes as he pushes off of there, I had dinner with him. Another cool fun fact I tell my daughters, but now I tell them I'm on the back of a book, right? So I get to connect all of these things. And he looked at me in the eyes more than once and said, Scott, I can't do that again. Humans have never been past the backside of the moon. A million miles away, they just have to get this. It has to work right the first time that it goes on orbit. Pretty humbling to have the last person who touched Hubble tell you you really have to get it right. I also had Senator Mikulski tell me that in Congress several times. So a little bit of a balance there. So this is the mission of what we had to do. So our solution was to build a segmented mirror. So this is an interesting picture because the first picture I showed you, the mirror was bigger. Now you're saying, what happened to that mirror? It looks like there's 12 segments, not 18. Well, there's 2 wings that are folded back with 3 and 3 mirrors on either side. So all of a sudden now, that fits in a 5-meter fairing. The second mirror is stowed up. But now you have a different perspective of that giant parasol that's underneath it called the sun shield. 80 feet long by 40 feet wide. Where does that go? You're going to see a little video that compresses this. That's your parachute, folks, that you're packing before you jump out of the plane. Your life on the line there. In our case, a $10 billion telescope if it doesn't deploy successfully as it's going 1 million miles away from Earth. I have some incredible journeys to share about that. But one of the things I want you to know is, what does it take to build a Webb telescope? It takes people from around the world. It took over 400 companies, 14 countries, 3 space agencies, 300 academic scientific institutions to build the Webb telescope. Imagine in each of your industries. Many of them are competitors, right, at times where we're vying for the same things, that have to now get on the same field and all row in the same direction, whatever analogy you have to use. Imagine you have to rally every one of your suppliers, every one of your competitors, and their competitor supplier to go lead and go do something. That's what it took to do Webb. I mean, it's like trying to get the Yankees and the Red Sox to do something better in baseball, right? I mean, you can laugh at that. Come on, it's New York. All right, so go in there. So it was an amazing team journey as much as it's a technology journey. And the connections that you build in that also last forever. The connections you made today will last forever. The connections I made at the Bedford Playhouse are going to last forever. So let's talk about the people and let's connect the themes here today. Here's an example, again, of lucky people who got to touch Webb. Some of them, like that person in the lower left-hand corner, probably did something on Webb for the very last time. Put a cable in its final place and never be touched again. You know, put a bolt in, put a fold into a thing. Well, that sun shield, which you saw better in the other one, should be folded up there. I love the compliments of what I read in Sheena's book there. Well, our head for the sun shield was also a sailor. So when you talk about something that has 90 cables and pulleys and has to fold up precisely such that at some point in time, I am talking about nanometer precision on the scale of things that are 80 feet long by 40 feet wide, because if you're off by small dimensions, you can end up with a snag. You can end up changing the tension in that line such that you can't reel it in, or when you lose slack, it's the worst thing you could do in a cable. Turns out sailors know about that, right? You don't want to get that thing hooked on something. You know, probably some people grinning in the room because I've been out there on the boat. I get seasick. I would not know how that works. All I know was Jim Flynn was able to bring the experience, as much as he was an engineer, from a practical world into literally designing one of the greatest deployables that humankind has ever built, this sun shield without it. No, by the way, we're folding up membranes, these thin layers, 5 of them, that are 1/1000th of an inch thick, so that they can fold. Greatest question, literally to this day, 12 years of giving speeches I ever got asked was by a 10-year-old. Right? So I'm in my daughter's science class, and I'm like, we got 5 membranes, 1/1000th of an inch thick, and they could be torn, and they're very fragile. We're going to fold them up, and a 10-year-old said, why don't you just make one membrane 5 times thicker? I'm like, whoa, geez. But I was really quick on my feet, and he had a piece of paper. I said, take that piece of paper, fold it, make a paper airplane, and throw it at me. He goes, I can't do that, I'm in class. I said, I'm running the class now. Throw a paper airplane at me. So he took this little piece of paper, he folded it up, and he threw a paper airplane at me. I said, now rip the cardboard off the back of your notepad, fold it up, and throw a paper airplane at me. Crack, right? You know, thick cardboard. I said, can't fold something that's too thick. So we needed 5 membranes, right? We needed to make 5 thin things that we can fold. So I was really quick on my feet. But I really want to credit that 10-year-old, right, for putting me on my toes. But it just shows how you have to keep thinking about things from different perspectives. So there's an inspiration. the same time, when we're putting those membranes together, they have to be held together. Otherwise, the flapping nature of a violent rocket ride destroys things, right? Unless they are rigidly put together. We have 178 release devices, actually meant to hold it together, but release on orbit. That's one subset, about half of 344 single-point failures in the Webb design. A single-point failure means there is no other way for it to work than its intended design in that thing. If it doesn't work, that part of the technology doesn't work, and most of them could have been mission-ending. To land Curiosity on Mars, 90-something single-point failures. To do a typical spacecraft, maybe 10 or 12. 344 single-point failures. But as we were putting the pins in the membranes, 5 membranes folded 10 times, that's 55 holes that I have to put a pin through, because you got to count the other layer in there, right? So it's 5 times 11. You have to put a pin through that had to be perfectly aligned. And the very time that we fold it, when the pins would drop through, they would nick the corner of the hole. And if you're not old enough to know 3-ring binders, then you put a little reinforcement on that hole there when the paper comes out. Come on, old people, laugh in the audience, right? So we got little tears on there, and then we would deploy it, and we'd be left with a tear. And we're like, this is terrifying. This is our only set of membranes we have, right, that we're going to fly. So we were able to repair those, and we said, we can't have this happen again. We can't have it on the last time we fold it. We had to align those holes before we put the pin in. And it was a fisherman on our staff, a technician, non-degree technician, created a thing called the squid jig. He goes, why don't we just go at it backwards? When we take this little thing, I use them like as a lure, and it's like a little octopus looking thing. It's very soft and has like these little 8 tentacles in there. And if we put it in, it'll start thin and it'll spread itself out. And we'll just pull it backwards. That'll line the holes, and then we put the pin in from the other side. That fisherman enabled us to save how we stowed and deployed these 5 membranes in there. And he was empowered to say that thought and not feel like a fool in the audience too. Right? You can imagine how many people have that thought and say, I'm not going to say that sounds silly. Why do they need me? They got a PhD in the corner solving this problem, right? You know, and no, but he opened his mouth, he talked to us, and he solved that problem. Of all the people that it took, I just want you to know this journey started in '86 as a cocktail napkin. The program was won in 2002. So it took 20 years to build it, and many of those were done 6, 7-day work weeks. 3 shifts a day, right? People that were around the clock, right? Handing off from others information so that we can, do that. The other thing about this final flight hardware, though, is we wouldn't let people use the flight hardware for the first time to learn. We literally built an entire membrane off to the side. You had to go in the practice field. You had to fold the membrane there before you would ever come into this audience in there. So we gave our people a chance to iterate through and learn. Learn for the moment that had to be perfect, but we gave them that chance to iterate. This is just a short video that shows that giant telescope, again, 40 feet wide, 80 feet long, 40 feet high. It just folded up a lot quicker than we did on the ground. It went into the top of a rocket. Then we're going to show this animation really quick as we launch. And imagine Christmas morning, we launch, we get on orbit. We are now journeying 1 million miles away from Earth. Solar ray comes out. The antenna to communicate to ground comes out. The sun shield opens as a clamshell first. The telescope separates so that it can be pulled tall underneath it. A deployable on the back to balance our solar shield effects comes out. Nested boom segments telescope out, pulling the 5 membranes on one side and then on the other. So now we have our length, we have our height, we have our width, but we have these 5 membranes collapse. 90 cables, then tension, and pull the 5 membranes apart. The nose comes out that bounce all the photons back. The mirror comes out on one side. The mirror comes out on the other side. 14 days later of holding our breath on orbit, from Christmas Day to that, to within minutes of the original timeline we planned, we were deployed on orbit. And we were about 1/3 of our way journey, and then we spent another 15 days, 29 total, getting to Lagrange point 2, 1 million miles away to start filing this mission. So what happens then when you get 1 million miles away and you get a telescope this thing built? Well, you look at Hubble and its iconic mirrors, and then watch that. And there's the eyeball of Webb 100 times more powerful. You look at Spitzer, the greatest IR telescope in space there, And then look at how you resolve that. Let me go backwards again and then show that again. That is one of the most iconic pictures of Hubble, but opaque to the light inside of it because it's an optical telescope. Infrared peers through. You look at an infrared telescope and you put up something 300 times more powerful, and you resolve tens of thousands of galaxies with information that humankind has never seen before. This came out on July 11th, and a little funny story there is supposed to come out on July 12th when I was at Goddard for the science reveal for Webb last summer. Remember, we're still in our infancy, folks. We haven't been on orbit for a year yet, and we're already in awe of what we saw. This view was shown by President Biden on July 11th because he stole our glory. He goes, nah, I want to show that. So literally 2 days before, Omar's here, my comms lead, we're all prepped up. We're at Goddard. I got Dr. John Mather. We got the Nobel Prize winner. We're all ready to do this. And like 2 days before, it's like, nah, the White House is going to show these images first. All right, go have your fun. We're still doing our event on July 12th, right? So on July 12th, we show what's called the cosmic cliffs. And you just watch us now peer into the universe, into this time machine, at a greater level of perception than humankind ever has been able to do before. And then we go into literally a practice run, and this is Webb's deep field. 30 years of Hubble, and in the first 12 hours of deep field view, Webb broke the record for the oldest galaxy ever seen. 14 days for Hubble to do that, as the head of the Institute got laughed at when he was said, let's program Webb to look at a dark spot of the sky. Because what do you tend to do? You tend to want to go look at what you already know and then find more information about it and learn better, right? It's a natural curiosity, right? Just keep learning more about what you know. Imagine the courage, and there's what's called director's time. I think it's 5 or 10% of the telescope's time could literally be directive. It's outside a competitive process. The head of the institute gets to make a decision. And he said, stare at a dark spot of the sky, basically a straw-to-straw look. Go out there. Let's just look at that. 14 days of telescope time. You know how valuable that is, how precious that is? And Hubble does a 90-minute orbit. It only can look 45 minutes. It's behind, the Earth. It's in the sun. It's in the shadow, just so you know. And when he did that, he resolved the Hubble deep field with 10,000 galaxies in a soda straw look. And he goes, now imagine what the entire universe looks like. But he was laughed at for thinking that. Sometimes look where you're not supposed to look to go find ideas, right? It's incredibly powerful. So we broke the record. We got gravitationally lensed, galaxy. We got all kinds of things that you can ask me 100 questions on, and I'll give you an answer. And none of them may be true because I'm not a scientist. But I know the pictures look really cool, right? And what we did was we were able, and it wasn't that Hubble was weak. Again, this isn't about knocking what came before. Hubble's design was limited by the wavelengths it looks in. All of the light, I promised you a science lesson, the light that came out in the ultraviolet and in the optical, what our eyes see, what Hubble sees, that we're at the start of a 13.5 billion-year-old star, now we're no longer in that wavelength because the universe is expanding. Wavelengths stretch. They call redshift. So we're expanding, so all of the ultraviolet light is now in the infrared. It's a real trick of Mother Nature, because now it's harder to find, because in infrared I got to compete with all these other IR sources. But that shifting of it, also, we can predict that, right? We know now how the universe is expanding, at least we think we know, until we learn something else. So that's why we had to build Webb, to find a chapter that there is no other mission, and you can't do it from even the biggest ground telescopes, because why? Our atmosphere filters some of that light. It just never gets to it. It doesn't matter how powerful you are if it's on the other side of the wall, right? In this case, the atmosphere. And then we had this image of the Wolf-Rayet star, and this one is about a sun 15,000 light years away, that's 30 times the mass of our sun, that has already shed off enough material to create 10 more suns, the equivalent of our suns. We're seeing this generation of star generation. We also see how stars die. The other cool thing in there to make you guys smart, right, is if you look at these, the big star images and the ones that have the primary 6 points that are in there, the very vertical line and then the X, that's the diffraction spikes of our hexagonal mirrors. So you will always know you're looking at a Webb picture if you see those 6 spikes. So you can tell your friends, oh no, that's a Hubble picture if it doesn't have it, right? So now you can distinguish this. Dennis Overby just put a couple of days ago in the New York Times a picture of Webb. I didn't have to read the caption. I could see the diffraction spikes. And then the fainter ones, that's the horizontal, are our struts that are necessary to hold a secondary mirror that obscure certain photons. But then I told Sheena I'd bring the closest that I could to have current stuff. This is lighting up the scientific industry right now. So this is a star called Fomalhaut, and in there's these belts that Webb has never, that other telescopes have never seen before. All of those inner rings don't exist to the capability of anything else. You know what we're seeing here? This is about 2 times as wide as our own solar system. And where those dusts form, that's how planets form, folks. That's how planets form. As a matter of fact, one astronomer was on Twitter, that little bright spot around just under kind of 3 o'clock, 4 o'clock, where it's a little brighter on the outer ring there, it looks kind of a little bumpy there. I think that may be a planet forming. And we're seeing this. We're finding chapters that humankind has never seen before. It's absolutely unbelievable that we built an instrument and put it into space 1 million miles away to do that. And then this is kind of one of my favorite pictures, though, because this is what folks look like on July 12th. That's me in the corner. Oh, by the way, was anybody up Christmas morning? You can lie to me. I'll raise your hands. And watching the Webb launch? All right, yeah, some of you lie to me. Good. But so Christmas morning we launched, but it took us 6 months to calibrate, right? To get to orbit, to get ourselves thermally stable and do that. When we launched, I'm the person on the left there with the bald hair, not the person sitting down. That was our last deployment at the Space Telescope Science Institute. At the time of launch, if you go rewatch the replay, the person who's doing the countdown, we launched from French Guiana on the Ariane rocket from the European Space Agency, a NASA-ESA partnership. And I was down there, and the launch director, who's counting down in French, however you can do that from 1090 and doing that stuff, and his name is Jean-Luc, and my daughters keep saying, Dad, how come they keep calling you Jean-Luc? I said, because that's the French guy named Jean-Luc, but if everybody thinks it's me, that's awesome, right? No, I'm the other bald guy. Look for me on the other side of the room, right? And when the cameras came on me, people are complaining, why are you on your phone? I'm like, because I'm texting my daughters that I'm not the other bald guy, right? So that was more when I was at the Institute, but then there's around the globe, students sending us pictures, people celebrating in the conference room, Coldplay concert, showing this, Times Square. But in the left corner, folks, that, as a Jersey kid on the other side of the Hudson River, that's the Empire State Building lit in gold because of the gold Webb mirror. I got to tell my friends, go outside, look across that river, see the Empire State Building. That's for the dumbass high school kid you went to school with and a team of thousands of others that built a telescope that has a gold mirror. Be pretty darn proud today, right? When you can get the Empire State Building lit up. So I talk a lot because it's a fun thing to do, but I want this to be interactive. So I intentionally went through those charts at a reasonable pace to share a tremendous amount of information, which I am obligating you to share with at least 10 people. That could be one cocktail hour and all 10 standing. I'm not saying 10 instances of one person at a time. There's not just man-to-man defense. I want you to share what you heard. But you want to learn more of what you heard, you got to ask questions. If you say it, I'll repeat it.
By chance, right here, there's an article from the New York Times about 2 weeks ago about the Atacama complex of telescopes.
Yeah. Oh, thank you.
They talked with them about the question of both Hubble and Webb, and said, what are the advantages and what are the disadvantages? And one of the advantages they, of course, said that both Hubble and Webb have is that they're, of course, farther out. But the shortcomings are that their apertures can never get any larger than they are, and they're too far away to have the technology change. Whereas these telescopes that are land-bound can do it. But what interested me was the concept of the aperture, because you talked about 6.5 meters for the Webb.
Yep.
And they're talking now about one that's going to be about 40 by comparison.
30-plus meter telescopes on the ground.
Can you talk about that in terms of the differential from the, because after all, what billions of dollars are spent on this, and there's a kind of choice that not only the NSF, but NASA and others have to make in terms of which ones to fund and why.
So great question. So let me just give the backdrop, right? There's ground telescopes, Hawaii, many other places, the Atacama Desert, which I had a chance to go to, but you're living at a high altitude. So you got to really, you have to acclimate right when you go there. That being said, we build large ground telescopes. We take trucks and bring segments, bigger than the top of the rocket up there. And it has an aperture that can be evolved, the instruments behind it. You're not going to do that a million miles away. But when they said never, I would have just faulted them at that moment in time, because we were never going to build a telescope bigger than the top of a rocket. Turns out we did. Webb's segmented design is the first deployed, and not only deployed, it's an adaptive optic. It has mirrors on the back. We can perfect our prescription for over 20 years until we run out of fuel. So we will keep the sensitivity for as long as we could imagine, hopefully before the next thing. And the objective for the next telescope, now that you have to prove something in a revolutionary way to then evolve from it. And with the way things are going with robotics and maybe low Earth orbit also becoming even habitational, right? And cislunar space around Moon, where we're doing habitation modules. Northrop Grumman is doing HALO for NASA on there. The idea of building now a segmented telescope being proved out in a very hard way of being able to do it on the ground and then launch it and be successful is scalable to a segmented mirror where you can build rings around it after you overcome Earth's gravity, when you can perfect it. And if you do that with more actuators, you don't have to be as precise as you need to be on the ground, because you can build it and tune it in orbit. They do atmospheric corrections with their adaptive optics, right? It's purpose-built to deal with it. We don't have to defeat atmosphere. We use it to keep the telescope precise in terms of the surface figure. So I say we will be building scalable designs in orbit, and Webb was the first of a kind of showing we do it segmented. Next thing is, how do you build on it? Probably not Webb itself at Lagrange 2. You probably want to do that assembly closer to Earth, but then to do that and then position it somewhere else, you've overcome a huge hurdle. Sir?
Shown us that have surprised the astrophysics department.
Yeah. So what has Webb shown us that has surprised us? First of all, everything surprises me because I'm not an astrophysicist, right? The thing that is being challenged right now, everything has a model, and sometimes even Hubble, and he kind of laughed about it, or he dismissed his own Hubble. Einstein and Hubble had constants, right? They put plug numbers in there. So, well, when all the math kind of settles out, I need another number to make it happen, right? But the expansion of the universe and the concept of how these stars formed early on, and what size they would be, how fast they would grow, how they would accrete, and how go through a life cycle, are brighter and bigger, I'm going to use every simplistic terms, than the models had predicted would be in this missing chapter. So they either got to find out that the observation's wrong, or they're processing it, because you also have to go through that, or that equation itself that didn't predict that, right, is wrong. And what is that? And what often happens beyond that, and as much as you solve that, is you create serendipitous moments. What to me is the most powerful word in the English language is serendipity. It means it's an opportunity where you're not as precise honed on trying to solve something. You have a conversation with something, someone else comes up. I'll give you an idea, and a very off track from your question, but first of all, they're finding that the age of the universe maybe not being challenged, but the development of these early stars and then solar systems and galaxies is different. It's brighter. So why is that? They'll have to do that. But talk about finding serendipity. When we built and had to test our mirrors, we had to create and invent the laser interferometry to measure the surface of something to nanometers. That's the size of bacteria, right? Precision. In a cryogenic chamber, through a window, minus 400 degrees Fahrenheit. That technology is used now if you go to an ophthalmologist, if you get LASIK surgery. That is a spinoff, not because we intended to spin off medical advances, but because engineers design things and other engineers figured out how to purpose those things, right? Scientists, when they find knowledge that bends that, their thinking, or maybe breaks it and shapes it in there, they bring that back and then they create bigger concepts out of it. Right, and they do it. So that's the short answer, is that is most of us being challenged. The other part of the mission I didn't even talk about, but even though I mentioned the word is, are we alone, is we're interrogating atmospheres of other planets around other stars, trying to find an Earth-like planet by literally finding the photons that graze the surface of that planet. And if they go through an atmosphere, if it's there, they lose part of their information, right? Because the atmosphere, as our own does, sucks that out. We see a photon that goes around the atmosphere. We see one that goes through. We contrast those with a spectrometer, and we actually tell if there's signs of oxygen or carbon dioxide. So we're learning about how atmospheres are forming. And one day we're going to find an Earth-like one, I'm convinced. I just don't know when. So we go there, and then we'll go to the back. We'll go to back row folks next.
Thanks for everything. Great presentation. From a bit like a business lens, we often think about sort of risk reward, right? And when you invest in something, well, yes, it could be great, but what's the risk involved? And obviously, when this project was conceived, I'm just thinking about the 350 points of failure and budget overruns and doing this through a recession at some points and different administrations. I'd imagine there's a couple of hurdles you have to cross.
Listed a whole bunch of good ones.
Yeah, there's probably a couple of hurdles you have to cross. So how was the approach to risk assessment and communicating, hey, we should still do this, keep going forward, keep persevering? Certainly it seems like a feat of like, trust me, this is going to work at some point, but there's got to be, in the early days before you had the prototypes to show that this works. I'm just curious how you approached that and communicated that.
It's a wonderful question because survival during any journey, right? And while there's either detractors because they don't believe you, maybe they do believe you, but they want their money on something else. That's more of a sure bet, right? So it always goes back to the mission. We never wavered. We didn't have to of what the purpose was of Webb and that there truly wasn't a substitute. One of the comments I've made several times when I would visit with folks who had important say in what happened was, if you don't do Webb, you don't answer these questions. Let's just start with that. You're just going to kick the can down the road, or you're going to be the generation that breaks the continuums from when we wrote on cave walls, right, and gave names of deities, right, to star patterns out there and use them to navigate by. And now we know that there's planets around there, right? In my generation, we've learned there's a planet probably around every star, and there was no confirmed exoplanets, and there was 2, right, and it went in. So we always connected the vision. The other thing was, when we had our humbling moments, we always wanted to say, do we know why we failed, and did we find something that pushed a boundary that was unobtainable, or did we just learn a lesson that was solvable, time and money, right, being a part of that solution? And thank goodness, with the incredible, heroics we have, we never found that. And it would have been my obligation to be truthful about that, not just marketing and sales. And when I got asked the question the week or 2 before the launch, which I was getting ready to ask, how do you know Webb's going to work, right? And this is before, right? It's easy to sit at the podium when you win the championship and puff your chest up, right, and be pretty proud. Answer that question, right, before. And I didn't quite do a Joe Namath moment, again, for you local folks there, but he's the one who predicted he beat the Super Bowl Johnny Unitas in 1969. I'm looking at some young faces who are confused right now. Anyway, but what I said was, I'm convinced we did everything we could on the ground. Now we have to go run the script. So the last thing was, my team always knew mission success mattered more, because you have to have one more dominant parameter than cost, schedule, technical, and what it was. And that had we had to do another deployment on the ground, I was going to have the courage to say, we're going to have to do that, and it was going to take longer. And that could have been a moment where we were subjected and threatened to, is it worth doing it? Did you find something that was in there? So we, thank goodness, over 20 years, never had a moment where we said we didn't think we could do it. But we had very humbling moments where we said we have to try again. And then we came to a point where we said, we're done. We don't have to try anymore. We're ready to go. So it was iterative. It stuck to the mission. We were not going to launch $10 billion that didn't work for one of another $100 million, just to put things in perspective. You can't get myopic. Back room.
So you've said how precise everything had to be from the launch onwards. I'm curious, what was either the thing that went the least according to plan, or something that was unplanned that you had to deal with after the launch? Yeah, so the launch finality, the launch itself, and then the deployment, really, I'll just continue that out, was so darn successful. There were a couple things that got us, but let me start with the thing that amazed us the most. I didn't show in there, but if you go, whatever, YouTube and look, when we launched and separated from the top of the rocket, and then 12 hours later did what we call our mid-course correction burn, we have to fire our own rocket engines on the vehicle to get 1 million miles away, right, 4 times further than the moon. We don't launch on a Saturn V, right? We launched on an Ariane 5, which is pretty powerful, but 10,000 kilograms, the geostationary orbit, not the size of that. So we have to do a burn. Those burns were so precise, based on all of the study we did, that all the fuel we saved
to correct our orbit before we fired our rocket engines to have that right, direction of thrust. We didn't use a drop of it, and we increased the lifetime of the Webb from 10 years to over 20 years. We over doubled on day one the lifespan of the James Webb Space Telescope. So now we take that $10 billion and we have, what the amount is, or we double the utility of that. So that's the part that went precise. There was subtleties that didn't go right that were prepared for with a huge playbook of if everything goes wrong, what would I do? Would I fire the thruster to shine, shake something loose? Would I point towards the sun to warm it up? Would I point away from the sun to make it cold, to use CTEs? We had a huge playbook. Preparing for failure was the greatest way to be successful. We challenge ourselves to say, don't just tell me how it works, tell me how it fails. But probably the things that got us, I'll just give you one, it's more of a novel story than anything else, is the way that we point, one of the ways is we look back to our own star, very bright for us, and we use a sun sensor. And it was like Tatooine. The register was registering twice because we were pointed so good, it kind of read it, and then it read it again, and we thought there was two suns, and we didn't know which one to point at. So we kept going into what's called safe mode so that we wouldn't, misorient the spacecraft, worse yet, right, in another orientation. And it was literally because our performance was so good, better than perform, that we ended up registering something faster. So you think about that. And then we had to learn basically how to drive the car. It was a manual in orbit. We had to grind through a couple gears, right, as we learned it. So with that, it was literally the idea of something registering so fast. So it was pretty darn cool. So, and then time check of how many more questions. I'm going to look to whoever's hosting this when you want me off stage. How many minutes do I got? I'm going to keep going question until somebody gives me the hook. But let's go to the white gentleman in the white shirt there, or is there already a microphone up there? Okay, go ahead. Whoever's got the microphone. One thing that really stands out is about how long the project was. I'll repeat the question. Sorry, it's okay. Yeah. So how do you motivate a team for such a long cycle thing and keep them motivated and do that? I started with hair. And part of that is, truth be told, as the leader, I had to be the lightning rod for negativity. And I had to translate that into what it meant to the team and say, you could read the newspaper, but newspaper doesn't know how hard what you're doing. They know the headline, right, of what went wrong. And who doesn't know on Monday morning why that was a bad bullpen decision, right? So for me, I had to be a central point. I also had the privilege, and it didn't feel like it at some point in time, of being a long-standing program manager, right? 12 years I ran the program from 2009, which was 7 years into it, but going over a major hurdle. And my job was always to get to the team and actually find out, I talked about living in the success world. If you want to hide from your failures, you also hide from your successes. So we went out there and we were incrementally taking on victories. Our first Sunshield deploy was a big idea, right? And we put that out there. The first time an optic got tested. So we gave people incremental ways to celebrate, right? It wasn't just one major milestone. The other thing is we made it very visible at both NASA Goddard and at Northrop Grumman in Redondo Beach. We had windows into our high bays so you could see what was being built. We don't do that for our spacecraft. This is very unique for us. And we used to have all these security standards that said you can't bring anyone on campus without going to the building first, getting a badge. We also, well, who's going to do that on a Saturday? Security's not even there, right? They're trolling the parking lot. I opened up the thing. I said, we got to trust our employees. We're going to let them go in this door, sign that person in, and we're going to let them bring their family in whatever they want 24 hours a day. So my team, not only that worked on it, that lived at the campus in there, 24/7 could bring their friends, their kids, their family who was in town visit, and go look at that telescope and then build that pride back up. I made it personal. I made it absolutely personal.
So,
okay, last question.
A connected question, the one never Bush question. So you had to work with distinct cultures, scientists, engineers, business people. How did you herd the cats? How did you make them work together? How did you manage the need for innovation and need to get it done?
So he talked about working with other groups. He mentioned scientists and engineers. I have a funny joke, if there's any scientists in here you may not like, but so the difference between a scientist and an engineer is, if a scientist is wrong, they get a Nobel Prize. If an engineer is wrong, you get fired. Because when you're wrong as a scientist, you just found out something that you didn't even think of, and you just discovered something and people love you. The engineering feat doesn't work, you know, it's there. But anyway, so you posit that. So yes, the scientists are the users of the instrument and actually creating that teamwork. What was most important to me was a team of folks who never get seen on the journeys of this. I had a Monday morning meeting for a half hour every week for 10 straight years with my communications lead, with my government lead, with my STEM and outreach lead who was making products for Scholastic that we anticipated was gonna be in books, textbooks, after Webb launched. And I shared with them what our journey was. They looked at how they would interface to the public, and we kept ourselves going. It had nothing to do with building a telescope in the high bay. It had everything to do with keeping a team motivated and connecting us to the world. And they would bring ideas to me. They would hear me describe things and ask me questions and make me think, oh, did I just describe it that way? That don't sound that good. I don't want to go out and say that to Congress next week, right? I mean, it was an inner group of people who helped me see myself as I was leading, and that were a big part of the team. And I credit them every bit as much as I do the engineers and the technicians that build this, because this was truly a journey that involved, you know, like I said, not only nations and institutions, but people in every background. So anyway, I'm happy to hang around. I don't know what happens after this, but I want to respect everybody's time that's in the audience here and say this was awesome. I charter you to go share, but wonderful. Thank you very much.
Thank you, Scott. Thank you all for coming. And a very, very brief thanks to Doug Main for all of his support, and to our superstar here, Sheena Iyengar. But thank you all.